So this is going to hold off before you. Instead of anyone or no, hold on to trying to go from the state, taking the rise up further in the back so that people can sit down and have it and see everything. And then also changes to the race. Okay, that makes it feel a lot better. Yeah. Let's go to the just a little superstition in my head. Yeah, that guy working for the take down there and
So instead of trying to move my virtual desktop to arrange it the way I want it, I just physically changed the monitor to the right. That's gonna upset somebody, trust me. So before Thursday, somebody's gonna email me going, so who made that change in Brave Hall and moved the monitor to the right hand side?
just type in, I have no idea, but like that when we got it last night, I liked it that, but. We just decided to keep it like that.
I mean, the podium is so small in terms of the surface area, you know, I hardly have enough room to set up my little laptop computer. We'll see. We got about 2 more minutes. I mean, are there any questions? Oh, I need to bring up my the spreadsheet because I think it turns out to be quite useful. So I'm going to bring it to. Okay, so this is a well, maybe not up here. I'll put it back. I think that's a good way to collect questions. You know, it was intended only for in-class, you know, question submission, you know, so that people who feel shy, they don't want to ask any questions in person, you know, can just type the question and use the form and submit the question. But I found that some people use it, you know, as a reminder of, you know, oh, we need to go over this topic, you know, in the following class, or I want you to go over the topic, you know, in the following class. I think that works out pretty good. So you guys can consider using that as a tool if you want to, you know, like you study and then you find out that, okay, I'm not quite understanding this thing here. You can just, you know, kind of turn that into the form that you saw earlier. But I don't want to show the form because it has the student ID of the person who submitted the question. So I want to maintain that privacy so that people do not, you know, get embarrassed or feel embarrassed, because I think anyone who study over the weekend and have questions to ask, it's all good. So any questions? I mean, we still got about 1.5 minutes or so.
How was your weekend?
How was my weekend? Well, on Saturday, I decided to drive to Oakland for a union-related meeting. So that was kind of fun and kind of, it was okay. And then on Sunday, it was Lunar New Year. So I went to San Francisco to meet up with my, you know, the in-law parent and also my own father. So there was that. Traffic was horrendous.
I would imagine.
Yeah. Well, I mean, it's not any worse than usual. I don't think it's any worse than usual just because of the New Year, especially because of Monterey Park. You know, I think a lot of people decided not to, you know, go out to celebrate this.
Wasn't the solar?
Sorry?
Wasn't the lunar and solar eclipse this past weekend?
Yeah. Yeah, it was Sunday. So Sunday was the New Year day. So the Lunar New Year calendar uses the cycle of the moon to keep track of year. And obviously, the number of revolution of the moon around the sun does not quite align with, you know, how long it takes for the Earth to go around the sun once. So it's not quite exactly 12 quote unquote months either. And that's why, you know, we have all those year of the rabbit, year of the dragon, and so on. So there are 12 animals, and then there are 5 elemental, you know, things that you add to the animal. So most people think they're all meaningful and there's a lot of interpretation and whatnot. No, that's just how they create a 60-year cycle. so that, all the rounding works out, so that, eventually, it matches up with the solar year based on lunar cycles. Yep. So instead of using the technical terms, the really complicated Chinese characters to have the 5 and then the 12, most common people cannot understand or remember those words. So they change those into animals, and also elements, so it's easier for people to remember. In other words, there's absolutely no meaning whatsoever behind the animal of the year. All right, so there we go. We got one person who's joining us from Discord because that person is sick. So I'm going to publish, a policy, regarding, when people get sick, they can join the class remotely. And I can allow each person like 3 times, okay, to be absent in person because of sickness, and instead, will be participating remotely. But every other rule applies unless the sickness is serious enough that that person cannot, participate. So I'll write it all up, so this way, it's not only applicable to that one person, it's going to be applicable to everybody. All right, so one more thing, and we are screen recording already because I set it up to automatically screen record. So that's kind of nice. All right, so we're ready to go. The first thing I'm going to go over, and by the way, this program is called Joplin, and Joplin is interesting in some ways. On the left-hand side, you see the markdown notation, and then on the right-hand side is the HTML rendering of the text. So for the most part, you guys only need to pay attention on the right-hand side, because I'll be typing on the left-hand side, because this beats me, actually, handwriting stuff, because my handwriting may not be as legible, and it also makes it kind of nice to write tables, equations, and stuff like that. So any questions about the use of Joplin? Everything on this screen is being recorded. So Joplin is being recorded, and later on, if I decide to use handwriting, as long as you can see on the projector, it will be recorded. Are we good so far? Any questions? No questions? Okay, well, then we'll go ahead and start to answer the questions from some people over the weekend. And that's just my Outlook. So I'm gonna close that out so it doesn't distract us. There we go. All right, so getting back to here. So one question is, can you please go over section 3.4.3 or question mark? That sounds a little confusing, but 3.4.3 gives me a starting point, and it didn't say which module either. So it's kind of like saying, let's meet up on First Street, Davis or Sacramento. But I think I eventually got it, okay, because 3.4.3 of the first module that we talked about, is I gave you guys an exercise for that. So from the context, I think it's that one. It is the exercise that you gave us to do. I couldn't figure it out. It gave me a headache. It wouldn't be the last one either. I mean, seriously. I mean, this is the beginning of this class is really just we're just in my context, from my perspective, we're really just easing into the material. So later on, it will be migraines, and things will progressively get painful. Hopefully that is not the case, but so I'll go ahead and try to answer the question. So if I scroll down, I have already prepared a little bit for that, because the equivalency is to say X or Y, which is this column here, is the same as X NAND Y NAND Y. That's basically what section 3.4.3 of the first module that we talked about on last Tuesday was about. So the question is, how are we going to work this out? So I'm going to fill in the table, right? That's what we're going to do. So as I do in the table, I'm going to use X here to kind of direct your attention because I want you guys to look at the right-hand side so you don't get, kind of confused by the markdown notation here. So what should go in place of X here? This is X or Y. That little V symbol is the mathematical symbol for disjunction in mathematics, but it just means bar from your perspective. So what should I put here instead of X? It's a false. Okay, so what about this one here? It's a true. What about this one? It's a true. And what about this one? It's also true. Very good. Okay, so now we have confirmation that you guys remember what disjunction or logical OR is. Okay, which is great. Okay, that's good to know. So we're gonna work out X NAND X next. Okay, the next column is X NAND X. So this one depends on whether you did a little bit of review and studying or not, because the truth table of the NAND operator was already discussed on last Tuesday / Thursday, because I think I finished one half of that, and then the other half was finished on Thursday. So what should I put here instead of X? True, very good. So what about this one here? True. And what about this one? Wait. This one is also true because it is a negated AND, which means if at least one side has a 0, the AND, the regular AND, is going to be a 0. But since this is a negated AND, it's going to be negating the 0, which means we get a 1 here. This is
not and X. It's X with itself, right?
it is. It's basically negating X itself. Oh, right. You're right. Okay, so I was wrong. Sorry. I wasn't paying attention. I kept telling my students, if I were to take my own class, the best I can do is probably a B. So don't feel a bit too bad. All right, so you are correct. I did make a mistake here. This is supposed to be a 0 because we are only using the value of X, not XY. That's what I was thinking is X and Y. Nope. I didn't read the question carefully. All right, so the other X is also going to be a 0 because we are also just, because it is also true, NAND true, and that should be a false. So are we good so far? Am I not confusing you guys too much? Okay, all right. So we'll work on the next column, which is Y NAND Y, which is the same thing as not Y. Okay, hold on a second here. Okay, Tech just said something, but how do you know that was true? That was valid, because what I said was Y NAND Y is the same thing as not Y. How do we know that? Go ahead.
Because we did a truth table on that.
Because we did a truth table and we established the equivalency. I think that one was done on Tuesday. So that was it. Okay, good job. Okay, so this is why it is important to get all the content down as soon as possible. So this is going to be a true, this is going to be a false, true, and a false. So are we doing okay so far? So now we look at the last column, which is X NAND X, which is referring to just the fourth column. NAND Y, which is referring to the fifth column. So we are doing a NAND operation between the fourth and the fifth column of this table. In other words, I'm really just asking, let me put the X here so I can divert your attention. So we are really just asking, what is true NAND true? What is that? False. That is correct. Okay, it is indeed false. And then on the next row, we are asking what is true NAND false. That would be true because at least one side is a false. Now we are asking what is false NAND true. It is also true. It's just symmetric to the previous row because we just swapped which side has the false. But we said that if at least one side has a false, the result of the NAND is going to be true. So now we get to the last row, which has false NAND false. And the answer is, yep, that's also going to be true. So now we can compare X or Y, which is the third column, versus X NAND X, the whole thing, NAND, Y NAND Y, the whole thing. And they turn out to be exactly the same for every single row. And this is why we can establish the equivalency between, I got your hand, the third column and also and the sixth column, not the fifth. Yes, go ahead.
So it doesn't matter what order.
What do you mean by order?
So if X, X,
NAND,
NAND, Y
yes,
is the same as Y, NAND, Y,
that is correct, because the NAND operator is also commutative. Okay, so I just said something without justifying or proving it. What did I just say? I said NAND is commutative. How did we know that? The truth table again, okay? So you can use the truth table to prove that NAND itself is commutative, which means you can swap the left-hand side with the right-hand side without changing the value of the expression. Is that okay? Yes.
In this class, is it required to only use truth tables to establish validity, or can I use like just properties?
Can you use what?
Like property, like for instance, you said the NAND is like if I had A and B, that's equal to B and A, right?
Well, this class is not about proofs. That would be CISP310. So in this class, I only do the proofs because I think it is important to tell you guys how you can make sure that I'm not telling you something that is not true. Like earlier, I made a mistake here because I thought this was X NAND Y, so I gave you the wrong value over here. So I'm trying to kind of give you guys the tools so that you can independently validate the claim that I'm making in class. And and the use of a truth table to prove commutative in this case is something that all of you can do, because it is just looking at the table and go like, oh, okay, so that is the same as that. Okay. All right, so is that question done? Are we good so far? All right. All right, I'm gonna move my stuff here, otherwise I'm gonna trip over that. There we go. All right, so the next question, there's another question that somebody asked. Can I please go over base 2 conversion, but in opposite direction? So once again, the question is a little bit ambiguous. I hope the person who asked that question did not feel that I'm criticizing, but it really is just not very clear because I don't know which direction this part is referring to. And therefore, I don't know what opposite direction, what is it opposite to? So that's okay. I'm just going to go over both directions. That will cover both directions. So it will cover both possibilities. All right, so this is what we talked about in class. Okay, we tried to express 18.875 in as a base 2 number. So what I did was I was basically remember the currency thing? Instead of $1 bills, $5 bills, $10 bills, we have 1, 2, 4, 8, 16, $32 bills. And then instead of quarters, dimes, nickels, and pennies, we have half dollars, quarter dollars, $8. Remember that? Okay, so that's when we look at that amount, which is 18.875, and then we ask, okay, if we are just looking at this as making change for that specific amount, how many bills do we need for the 16? How many for the 8? How many for the 4? How many for the 2s, and so on? So do you guys remember that process? Are there any questions about that specific process of how to figure out, yeah, we need 1/16, and then once the 16 is taken care of, we don't need an 8, we don't need 4, but we're gonna need a 2, and so on. So are there any questions about that process? All right, so I think I answered one possible question based on what I was asked. So the reverse is I give you a binary number, okay, 1001.101. I give you a binary number, and I'm asking what value is the binary number represent? That's basically the reverse of the question. So The most important one is this one over here, or I should come to this side and one to this one here. So this one is special because it is immediately to the left-hand side of the point. What does that mean?
It is the base is 2 to 0 power, which is 1.
Yep. So let me repeat, rephrase what you said. So this one here is saying that we have one of whatever base we're choosing to use. In this case, it's base 2 to the power of 0. So that means we have 1 of 1, 0 of 2, 0 of 4, and 1 of 8. The position of each digit is corresponding to saying, okay, how many of 2 to the power of something that corresponds to that particular position? Is that okay? All right. What about the other side of the point? What about this one over here? So let me get back here because the person who's online may not be able to, won't be able to see what I'm talking about. What about this one here? It is telling me I have one of what? 2 to the power of -1. That's right. Okay. So when we move to the left-hand side, it's increasing the power. When we move to the right-hand side, we're decreasing the power. We can go negative. There's no problem with going negative. Are we doing okay so far? Is that okay? So what value is this number representing? This is a base 2 number. We know it's base 2 because of the 2 in parentheses, which can also be a subscript of 2, but it's just indicating the base that we are using. So we got 8 plus 1, so there's 9. This is a half. We don't have a quarter. We have 1/8 here. So it's 0.625 from the perspective of base 10. So this is 9.625 in base 10. Is that okay? Are we okay with that process?
Yeah.
Yes. Okay.
While we're doing this, can you go over the base 7 conversion that you did?
Yes. All right. So, all right, cool. Base 7, we can start a new number because I think I chose a fairly bad number to convert from because it turned out to be just 300 because I found a value that is just 3 times 49 in that case. So we just have to avoid a number. Anything that is even is not going to look like that. So we'll try 222. And once again, you can focus on the right-hand side of the screen, because I'm just using the left-hand side to specify the value. All right, so I just want to make this super clear. This is 222 in base 10. So this 10 as a subscript tells me that this is a number in base 10. Is that okay? So I'm going to look at this and go like, I want to express this number as XYZ, but it is in base 7. So I'm looking at X as 1 digit, Y as 1 digit, and Z also as 1 digit. I need to figure out what those are supposed to be. So this is kind of what we are going to talk about in today's class, but we can try to solve this kind of more intuitively, and then we go back to the math behind the whole thing, and I'll give you the equations to do the same thing. Is that okay? So once again, what is Z representing? Z is representing the quantity of 7 to the power of 0. Very good. Okay, so I heard 1, 2, so I think that might be referring to 7 to the power of 0 is 1. So both are correct. Okay, 7 to the power of 0 is 1. So Z is representing how many 1s do we have? Y is representing how many 7s we have, because it is corresponding to 7 to the power of 1, because this is digit 0. Z is digit 0, Y is digit 1, and then X is digit 2, which is corresponding to the quantities of 7 to the power of 2, which from the perspective of base 10 is 49. Is that okay? So we have to somehow represent 222 as something times 49 plus something times 7 plus something times 1, with a restriction of that something can only range from 0 to 6, not 7, because in base 10 you can only use one single digit to represent from 0 to 9. 10 itself requires 2 digits in base 10. Is that okay? All right. So we always work from the most significant digits, which in this case is X. So we want to find out, okay, give me as close as possible, just, the multiplier of 49 in order to get close to 222. It has to be less than or equal to, yes, 4. It'll be 4, very good, because 49 is very close to 50. So 222 divided by 50 is 4 point something. So 4 is a good value. Okay, so that means now we will say this is 4 times, okay, 4 times 7 to the power of 2 plus, okay. So now we want to figure out why. So 49 times 4 is taking care of 196. Okay, now you don't even have to, you don't need a calculator to find that, right? Because you know the trick. Because 4 times 50 is 200, and 49 is just 1 less than 50. So that's why it is 4 less than, 49 times 4 is 4 less than 200. So that's all the mental arithmetic tricks. Okay, this has nothing to do with mental capacity. It's just that you have to know the tricks to do that. All right, so out of 222, 196 is done. So we got what, 26 left. So out of 26, how many 7s do we need? And how many 7s can I fit into 26? 3 of them. Okay, so we'll go ahead and write that. So we have 3 times 7 to the power of 1. And once again, you can focus on the right-hand side because the left-hand side looks like a mess. So that will take care of 21 out of the 26. So what is left over? We got 5 left over, and now we have to specify the number of ones to specify 5. That's an easy one. So we have exactly 5 for that. So 5 times 7 to the power of 0. So that means if I want to express this as a base 7 number, it'll be 4, 3, 5 in base 7. Is that okay? All righty. So let's go ahead and take roll today because it's important to take roll, as much as you guys are thinking, but we are in college, Tech, we're not in elementary school. Yes, I know that, but it's still important to do it. So give me a little bit of time to set up the roll taking activity, and I'm going to use this one here. I'm going to recycle this one. So I'll go to edit. Change the date, 2023-0124. And I need to change the format of the so-called quiz. I think this still beats passing a piece of paper around, especially when there are gaps like this. This classroom needs to be, huh?
I was going to say, we don't want to keep the same password for this one, last one.
That's a good password.
It is.
I am going to use that. That's a very good suggestion. So I'm going to change the access code of the old password. Yeah. All right, so, but I also have to change the question because, before, the question, I just use a word. So I'm gonna have to change the format of that. And so I am in class today. And it's just gonna be a true, false kind of question. And once again, anyone who answers false is gonna be counted as 2 days of absences. Okay, let me save it first. Okay, I'm gonna click save and publish, so that will make it visible to you. So you can refresh your browser. And then the password is always gonna be here. It's just the old password using the camel casing.
So it's gonna be locked because it.
Oh, right, because I didn't set up the time. Right, sorry about that, I forgot.
They mean I can get that bus after 2 days of lecture.
All right, so there's no way you guys can travel back in time, I suppose. So January 24th. Yeah, what the heck, I'll give you guys like up to 6:10 p.m., so 15 minutes. I don't see anyone, walking outside to go to the bathroom, so I think everybody should be able to do it. All right, there we go. So if you refresh now, I think you should see it. And then the access code is the old password, and you can do it, if you type it wrong the first time, no big deal, just try to do it again. Check your caps lock. Yes. The first time. You may be the first one. And I'm pretty gentle, not using some symbols that are really hard for cell phones to enter. I have to press 6 keys just to get to that symbol.
You could do like alt 130, like use like alt characters. Somebody like the phones just can't do it.
Happy face, sad face. Yeah, what?
It's, yeah, it's lower the camel.
Oh, okay.
Because somebody said, why don't you use the old password? And so like, the old password is a good password. Literally, the old password is a good password. I think next time I'm gonna use the what password?
Yes, you could also use Defcon's code.
What's that again?
Said Defcon does hack the planet.
Oh, hack the planet.
Yeah, they could do that for one of them.
That would be interesting. Well, I'm waiting for there's a movie from way back, when your parents were very young. It's called War Game. Okay, the movie War Game. I'm waiting for a remake of that movie, based on the AI technology that we have today. So we just have to kind of push it, like 5 years ahead, and find out what AIs can do in terms of playing war games. Yep.
It would just be like the person would try to play the game and the AI would be like, yeah, I'm not doing that.
The AI will tell the person that person has failed the Turing test. I think that would be kind of funny.
But when the AI started going to war, would they follow the if their entire objective is to win.
And that's what is the whole purpose of winning, right? Alrighty, so are we good here? Does anyone need more time to enter the old password? No? Okay, all right. All right, so we are gonna go back to our usual boring topic. And I think I have addressed all the questions from the spreadsheet. So is this okay? Just how I derive your 437 as a basic 7 number, representing 222 to us. Is that okay? All right. So this is actually a perfect segue to the module that we are supposed to be talking about today, because that is values, numbers, and bases. So assuming that you have read this module already, so I am just gonna skip a little bit forward to I can get to this part here. All right, so without any subscript, it is by default in base 10. Okay, it's just because otherwise it doesn't make sense to have subscript 10 for every single number that I write in this class. So without any subscript, it's going to be base 10. So we have 16.375 here. And what is 16.375? It's 10 plus 6 plus 0.5 plus 0.07 plus 0.005. Everybody knows that, right? I mean, this is like super duper easy. But there's a pattern to it, because 10 is 1 times 10 to the power of 1. 6 is 6 times 10 to the power of 0. 3 is 3 times 10 to the power of -1. 7 is this, and then 0.005 is that. Okay. So what we are looking at here is something that I said already earlier in class. Each digit of a number is specifying a quantity of the base, which in this case is base 10, to the power of its own position. And in terms of position, the digit that is immediately to the left-hand side of the point is 0. That is position 0, which means the digit at position 0 is the one that is responsible for the number of whatever base to the power of 0. All right. So we got one person who's joining us in Zoom late today. See that. Give me a second here. All right. Okay, so getting back to this discussion here. So with this one here, so we look at this and go like, well, this works, but only for that number, 16.375. So is there a way to generalize, how we figure out the value represented by a number? And the answer is, well, just have to establish some conventions. The convention is discussed in this paragraph. I changed it just a little bit. I think I replaced one sentence with 2 sentences. So in this case, I'm using the notation. Okay, I forgot to use spell check. Notation, not no dashing. Notation D of I to represent the digit that indicates the quantity of 10 raised to the power of I. Is that okay? Does everybody understand what is D subscript of I? Okay? Okay? All right. So in the example, I even use a few examples here to illustrate. D of 1 is 1. D of 0 is 6. And then D of -1 is 3. D of -2 is 7. And D of -3 should be 5. So that's just an example to illustrate what that notation is about. So are we clear on that notation? Yeah. All right, very good. So based on that notation, so now we can say the value being represented by a number, which is b in this equation here, is d subscript 0 times 10 to the power of 0, d of 1 times 10 to the power of 1, d of -1 times 10 to the power of -1, and so on. Okay. Are we okay with that equation? Because I don't know how many significant digits are in that particular number, so I just go like, yeah, there may be more. There may be more things that you have to add to the sum. Yep.
After that, is the bottom number where you start and the top? I mean, is the bottom infinity where you start and the top infinity
Right.
where you end?
Yes.
Okay.
Yeah. So typically, the bottom number in the sigma notation is smaller than the number on the top because you have a for loop, and the for loop is supposed to increment whatever index you choose to use for that loop here. So I is kind of like the variable controlling a for loop. This is where you start and this is where you end. And I chose to use infinity because we don't know how many digits we have in a particular number. So for the most part, like for the example here, we do have a digit here. It's just 0. So d of 2 is 0. D of 3 is 0. D of 4 is 0. They do exist. It's just that it doesn't make a whole lot of sense to write all the leading zeros, and all the trailing zeros are meaningless as well, because if there's a 0 after the 5, and then there's another 0 after that 0, and so on. But because they're all zeros, they're not contributing anything to the value. So typically, we don't have to write it out. Is that okay? But in the case of pi, okay, if you want to represent pi as a base 10 number, then you do have an infinite number of digits, on the negative side, because it is a irrational number. Just like the number of days in a year, the number of days in a month, the number of months in a year, and so on, all of those are irrational numbers. Are we okay so far? Okay. Hmm? Why are they irrational? Because the way the Earth revolves around the sun, yeah, the number of self-rotation that it takes to go around the sun, once is a irrational number. It's the same reason that pi is irrational.
Because the rotation isn't circular.
Because there's no reason for it not to be irrational.
Isn't irrational not able to be defined by a fraction?
Yes.
So wouldn't the number of days in a year be 365 and 1/4?
I was waiting for someone to mention that, so I can correct that.
Okay.
So every 100 year, you have a leap day, right? And then every 400, I think, you take that leap day away. And then every 2000, if I remember correctly, you have leap again. All of those things are for the approximation of the actual number of days in a year. So the number of days in a year is really not 365 1/4. It is 365.24, blah, 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 blah. Okay, it's an irrational number, but since we count the number of days, so we are not using star date or anything like that. So that's why we have to use the quarter to approximate. Every 4 years, we kind of have to bump up by 1 day. And then every 100 years, we have to bump it down by 1 day. Every 400 years, bump it up again. Every 2000, bump it down again. So if humanity can survive long enough, we'll probably have to bump it back up again, every 50,000 or something like that, just to approximate the actual value that we want to get. So that's a good question. I like that question because that kind of explains why we have leap years and then why sometimes it's not leap. Cool. Isn't that cool? I think it's kind of cool. All right. All right, so obviously I should be an integer. You can imagine an infinite number of leading zeros to the left and an infinite number of trailing zeros to the right. So that's why the range of I is ranging from -infinity to +infinity. Now, in reality, it doesn't work like that because your computer only has a finite number of bits or binary digits. So as a result, okay, when you look at even a 64-bit integer, it only ranges from 0 to 63. Right? But theoretically speaking, the value can go from -infinity in terms of the position to +infinity in terms of position. All right, so now we're gonna move on. And it's always a good thing to challenge our beliefs. In this case, we are asking, what about the other bases? Okay, if I give you a number that is in some other base, how do we figure out the value represented by that number? Well, that's easy. We have a 10 here only because we're dealing with base 10. So if you just generalize this 10 here, the literal number 10 to B, then we can deal with any base, okay? So B is representing the base that we are using. So in our example, in this class, we're going to use base 2 a lot. That means B is 2. Okay. In some examples, in some weird examples, I like to use base 7. So B is 7. But it doesn't change the structure of how we interpret the digits of a number in order to figure out what value the number is representing. Are we good so far? Is everybody kind of clear on what number is and what the value is and why they are two different concepts? Good on that one too? Okay, all right. So now we're moving on to the reverse direction. Okay, in other words, if I give you a value and I say, I want you to convert it into some base 7, base 5, base 4, whatever. How do we do that? So there's a little bit of reasoning. I'm not sure how many of you actually read through the reasoning part, but in the end, I give you an equation to figure out a particular digit of a number. So we're going to use the example that we had earlier to see whether that works or not. So what equation are we talking about? This equation over here. So this equation, if you give it b, which is the value that you want to represent, you give it a b, which is the base you want to use for this particular number, this equation will give you the digit at position I. That's basically what it does. It gives you a single digit at a particular position of a number in base d. So first of all, are we okay in terms of the purpose of the equation? Right? So the next question is, well, what is that weird looking bracket thing that is not exactly a bracket because it's missing the top? Are we running out of dark or black pixels? No, it's called a floor operator. Okay, so I'm not sure whether I explained the floor operator in here. Did I? Okay. Sometimes no, I did not. Okay, well, that's fine. So now that I have told you this is the floor operator, what are you going to do? Whip out your phone, go to Google, or use your Google Voice and go, what is the floor operator, right? Back, well, I just silenced my phone so you may know. Hey, Google, what is the floor operator?
According to Wikipedia, in mathematics and computer science, the floor function is the function that takes as input a real number x and gives as output the greatest integer less than or equal to x, denoted x or floor.
I don't need to teach the class anymore. Well, it doesn't even need Chat GPT. This is like just regular Google Voice, gets the answer. So once again, it is the largest integer that is less than or equal to whatever is in the floor operator bracket. Are we good so far? Yep.
Is it basically just a step function?
Basically, is it what?
Step function.
Step? I'm not familiar with a step function.
Kind of, yeah.
Okay.
That function is the function where I believe it's denoted with double brackets around y equals x with two brackets around it. And basically what it does is it goes as just the integer piece of the x variable.
All right.
Yeah.
So step function x, the step function of x is the greatest integer less than or equal to x. The floor function is written a number of different ways, with special brackets. So are they the same thing? It looks like they're defined exactly the same way.
Roughly, yeah.
They look exactly the same. There's one function that looks similar, but not exactly the same. It is the truncate function. So the truncate function means it'll just drop whatever is after the decimal point. So for non-negative values, the truncate is the same as floor, but not for negative values. Yes, go ahead. Yeah.
I think that would be just like taking the ceiling function for the value below 0. So it'd be like combining the two functions.
You mean the step function?
What is the truncate function?
Right, truncate is the same as floor for non-negative values.
Yeah, but with the negative values, it would be the same as ceiling.
Correct, that is correct. All right.
Yeah, from what I can tell, step function is kind of generalized, just a function that is a number of disconnected horizontal lines. Any function that can be written like that is a step function.
So it's non-continuous.
Yeah, it's
Okay.
not continuous and it's only flat lines.
Okay. I can see that. All right, so So are we okay with this equation now? Now that we know what that, square bracket without the top means, right? All right, so let's apply this equation to the example that we have just worked out, right? Remember the 222 thing? So we're gonna plug that in here and see whether we got the digits right or not. All right, so let me see what is the best way to do this. I'm gonna right click and copy and paste the text command. So this way I can copy and paste it directly into Joplin. And so you guys can see both at the same time. There we go. Isn't that cool? It's kind of like copy and paste. It is copy and paste. All right, so B is 222. And we want to figure out, what happens when I equals to 2, E of 2. Okay, that's the first thing we want to figure out. So, okay, so I'm going to carry out the actual computation here.
Can you do that a little bit, if I can?
Hmm?
Can you zoom in a little bit? It's kind of hard to see that,
Oh, because it's kind of faint.
Yeah, it's small.
I see. Let me see. Zoom in. With that, does it help?
A little bit, one more time. I think it's probably good. Yeah.
Yeah, I think the equations are harder to read because it's trying to render it, in the perfect way. So, and I think I may not be running at the native resolution of the projector. That doesn't help. All right, so we start with 222, that's B, divided by, the base, which is 7 to the power of 2, because I equals to 2. And then we have to take the floor of this. Okay, so take the floor of this. And then we have to proceed to mod it with the base, which is 7 in this case. So does that come out as 4? Well, let's do a quick calculation. 222 divided by 49 is 4 point blah, blah, blah. The floor of 4 point blah, blah, blah is exactly 4. 4 mod 7 is 4. So we got that. Okay, well, maybe it's just coincidence. We'll try to figure out what happens when I equals to 1. Okay, and this time I'll make it clear that we are dealing with the case when I equals to 1. So we still have the same value. So the 222 is still the same, except this time we're dividing it by 7 raised to the power of 1, which is just 7. Whatever the answer is, we take the floor of that and then we mod that with 7. Okay, we'll do it one step at a time. 222 divided by 7. Okay, divided by 7 is 3. And then we have a 1, 2, so it's 31 point something, 31 point something. Does that make sense? Okay, so 31 point something, you take the floor of 31 point something, you get 31 back, right? So you have 31 mod 7. 31 mod 7 is the remainder of 31 divided by 7. So 31 divided by 7 has a quotient of 4 with a remainder of 3. Because 4 times 7 is 28. 28 plus 3 is 31. Is that okay? All right. Ha! That works out. So we're going to work with the last one, which is, we are trying to figure out what is digit 0. What if I equals to 0? So we'll go ahead and take a look. When I equals 0, we are basically dividing 222 by 1. That doesn't seem very helpful. Well, it is what it is. Okay, so it's just 222. The floor of 222 is 222. So we have now 222 mod 7. So 222 mod 7, we have to divide it by 7. So we have 3, we got 21 here, we got a 12, there's another one here with a remainder of 5. And that is where the 5 is coming from. So this, yeah.
So the floor operator, you just use the return like a whole integer.
The whole integer that's below the decimal.
the largest whole integer that is less than or equal to whatever is in the floor operator.
So instead of using like decimals, we just use a floor operator to get like a whole number, right?
Right, because we only apply the floor operator to non-negative values in this class, so you can look at it as truncate. Yeah, so we're basically just losing the fractional part of a number. Right. So is that okay so far? I mean, you guys understand, how we went in one direction, which is, converting something to a specific base, which is what we are doing here. And then go the other way, which is I give you a number in the specific base, but I want you to figure out what value the number is representing. Are we doing okay in both directions? Right. Cool. We still got half an hour. I like it when we have time. So now the section 6 says, okay, Tag, you talk about all the strange bases like base 7, base 5, base 4. I thought this class is about computer science and we only use base 2. So what are we going to do here? B equals 2, right? B equals 2. Now we're dealing with base 2. So this is a general direction that I typically take. It doesn't matter what I'm teaching, is I would start with an example that all of you understand, like making change, looking at the base 10 number, separating the components of the base 10 number and stuff like that. And then I'll gradually generalize. I'll give you an equation like, okay, if we generalize our understanding of something like this, the structure is like this, okay? And then I'll give you the abstraction, all the way to the point where, oh, so this works for everything. But I thought we only cared about base 2. Yes, that's kind of true. So let's specialize in base 2. So I will do the specialization at the very last moment. So that's kind of how I try to explain things. It doesn't mean it's the best way, but it works best for me when I try to understand something. Is that okay so far? All right. So the process of generalization and abstraction is really important because if you think about it, that's what a program is. A program is an abstraction of how to get something done. So if you want to pursue computer science, you are really trying to be very, very good at abstraction. All right. So binary numbers is really easy to work with. So now base 2 numbers are interesting because when we look at the digits of a particular base, it will range from 0 to whatever the base is minus 1. So in base 2, we only got 2 digits or 2 values for each digit, which is 0 and 1. So that makes it kind of interesting in many, many ways. All right, so this section here is really just kind of go back and talk about base 2 numbers. So in this case, let's do a quick conversion here. What is this base 2 number representing? 1101 in base 2. So I'm just going to pick up one specific digit, and you tell me what power of 2 we're dealing with that. I will pick this one here. Okay, so let me move the mouse cursor to point to the one digit that I want you to tell me what power of 2 is this particular one corresponding to. 2 to the power of 2. Very good. Yep, that's exactly. So we now know that we have 1, 1, 0, 2, 1, 4, 1, 8. So we have 8 plus 4 plus 1, which is 13, which is also explained down here. All right. So section 7, kind of relates to how values are represented in the computer. It's not quite as simple as the equation earlier showed, because that equation doesn't show you how we can represent negative values. Right? I mean, let's take a look again. So we'll go and take a look at the sigma notation. This one here. Well, d of I is going to be between 0 and 1 for base 2, right? And even though I itself can go negative, 2 to the power of I is never negative. So that means the sigma can never go negative. So the question now is, how do we represent negative values when this equation here can never go negative? So that's a question that we'll answer later on, okay? There's one particular module that specifically just talks about the signed versus the unsigned representation of integers. There's another question, which is, where's the point? I mean, if you look at the representation, the examples that we have used, let me switch back to Joplin. So if you look at the example here, this point here is very important because it is telling us, it's separating the digit corresponding to digit 0 and digit -1. So that point is really important. But when you look at all the bits inside a computer, there are no points. It's just contiguous. So the question is, then how do we represent pi or an approximation of pi? How do we represent like 1/4 when there are no points, explicit points to specify and go like, yeah, on this side is the digit corresponding to 1, and on this side is the digit corresponding to what we know as 1/2. So we'll talk about that also later. That would be the module that talks about the double precision floating point number. Some of you may have some experience with this topic already because that topic used to be in CISP 440. And it is still in CISP 440 for some of the sister colleges, but we have modified ours to conform with the CID template. So that's why that particular topic is in CISP 310. Alrighty, so now we can move on to addition. So I think all of you are thinking, but I know addition already. Why do we need to talk about it? What is the point? There's no point in talking about addition. So this is about binary addition. Well, eventually it is about binary addition, but initially it is not. So initially it is about addition in general. So this is long, boring, okay? Most of you look at this and go like, do we really have to talk about this? So the answer is yes, okay? Because I want to extract the structure of how we perform multi-digit addition. And once I extract the structure, then I can apply that structure regardless of what base I'm dealing with. And then I can specialize and go like, okay, well, what if we want to specialize in base 2? Well, it turns out when we specialize in base 2, there are certain interesting operations that we can perform that makes it possible to be done using transistors. So that's kind of the overall arc. It's going to take us at least 2 lectures to go through all of this material. But we'll go ahead and start with this. So this is where I probably want to use my touch screen or my tablet because it's harder to make a table on the fly for this kind of stuff. So let me start that up in a second here. Oh, I need to do one more. All right. So what you're seeing here is Zernal++, which is a tool that also works in Windows. If you have a tablet PC, it's a great little tool because you can just kind of draw stuff and do handwritings, and it's free. So let me go back to my side, and let's see, where's my. There we go. All right. All right, so I'm just going to teach you guys how to add base 10 numbers. Okay, so we'll go ahead and start with, I'm just making sure I'm using the right color ink here. Okay, so we'll start with 237 plus 100 and, okay. Let's make it a 6 here, and then we get a 8 over here. There we go. I'm hoping all of you know how to do this because some people are going to say, well, we got calculators. I don't need to know how to add. Well, unfortunately, that argument can only go so far because by the time you graduate, the person who's gonna interview you for a job is gonna say, but the computer can do this already, I don't need you. So kind of keep that in mind, okay? Because that conversation may pop up. All right, so the way we do this is we look at 7 plus 8 and we go like, okay, what is 7 plus 8? Most people would say 15, but instead of saying 15, I'm gonna say it has a single digit sum of 5 and a carry of 1. Is that okay? And because we're dealing with digit 0, the default carry is a 0 because there are no digits prior to digit 0, so it has a 0, has a default of 0. Is that okay? Does everybody understand what I mean when I said single digit sum? It is the least significant digit of the sum, and then the carry is essentially the other digit of the sum. Okay? All right. So now we say, what about 3 plus 6? 3 plus 6 itself is a 9, but then 9 plus 1 is a 0 with a carry of 1. All right? And then we have 2 plus 1, which is 3. 3 plus 1 is 4. And then over here, we have 5 plus 0, which is just 5. So the answer is 405. Okay, you guys go like, I know that already. What is the big deal? So the big deal is we're trying to extract the structure of a multi-digit addition. So now the next thing I'm going to do is to say, okay, let's pretend that we are not looking at actual digits. This time we're looking at variables, each one representing a single digit. So let me give you the names of the variables. So we have x2, x1, x0. So each each one of these is representing a single digit of the first number that we are adding. And then we have y2, y1, y0. So that means, I'm just looking at this row here as x, this row here as y, and then I use a subscript to indicate which digit I'm referring to. So that convention we have talked about already when we talk about d subscript something. So this is just a way for me to specify x is a number, y is a number, but which digit do we want to focus on? Is that okay? So now we look at the next row. This row here, I just call Q. Don't ask me, I cannot remember why I chose to use Q to represent this row here. So this is going to be Q2, Q1, and Q0. And then the last one is K. Why is it K? Because K for carry. I know carry is supposed to start with C, but I used C for something else already. So that's why I have to use C here. So this is K2, K1, and K0. And then the last row is sum. So it's S. So we have S2, S1, and S0. And we're going to have a K3 here. Sometimes it's used, sometimes it's not, but I'm going to put K3 over there. So what I've done here is to convert an example that we are very familiar with, which is just base 10 multi-digit addition, into something that is more abstract. Because now I'm not adding specific numbers, I'm adding in terms of just variables representing the digits, because I want to extract the mechanism of how we perform the actual addition. All right, okay. So now I introduce you two functions, which is also in the notes. So I want to point out where you can find it in the notes first, just so that when you study, you know where we are what we are talking about. So we are now defining two functions. C is for figuring out the carry of two single-digit addition, and then R is our single-digit sum when we add two digits. Is that okay? All right. Well, you guys are all nodding, but I'm not really sure that you guys are fully convinced that this works out. So we're going to try this out, okay? So we'll say, what if x is 6 and y is 8, okay? So let me use my mouse pointer to point to exactly what we're talking about. So what if this is 6 and what if this is 8? So we're trying to figure out the carry of 6 plus 8. And this is 6 plus 8 is what? 14. Is 14 greater than or equal to 0? Yes, it is. So according to the ternary operator, we're gonna return the value of 1. And no one is asking me, I have never seen a question mark and a colon. What is that? Yes.
If the statement previous to that is true, it returns the first value, if it's false, it returns the value.
That is correct. So this is called a ternary operator. If the first component is true, then the second component becomes the value of the entire expression of the ternary expression. If the first expression is false, then the third expression becomes the value of the ternary expression. It is basically if then else in a single statement. If you have never been exposed to this operator, you will probably find it a little bit awkward to begin with, but then later on, you will probably find it very useful. Okay, I personally find it super duper useful. All right. And what about the R? What about the single digit sum of 6 plus 8? So X is 6, Y is 8, 6 plus 8 is 14, 14 mod 10 is 4. Okay, well, that seems to work out. Are we good so far of what is the C function doing and what the R function is doing? C is the carry, R is the single digit sum. All right, so keep this in mind when we switch back to Zerno, which is where I can handwrite stuff, okay? So based on that understanding, can someone tell me what is Q of I and how does that relate to X of I and Y of I said I, but I wrote 0. So how does that relate to Xi, Yi? Okay, I'll give you a clue. It's either the R or the C. Which one is it? It is the R. Very good. All right, nice.
Wouldn't it also be that plus the C from xi minus 1 and y?
No. The C doesn't. Okay, look at this 9 over here. So it is just the sum without taking into consideration whether we have a carry from before or not.
Okay.
Okay, that's important because we normally do not write it. So normally when we perform multi-digit addition, we don't write out the Q because it's intuitive that we can just figure it out. But when we want to generalize the method to the point where we can create a circuit to do it, we have to make it explicit. And that's why Q, the role for Q, is explicitly represented in here. Okay. All right. So if that is the case, I will do, what about S of I? So S of I, seems to relate to Q of I and also K of I. So once again, is it R or is it C? Okay, so what value can C return? What is the range of values that C can return? 0 or 1. If you look at the sum row, that doesn't look like a 1 to me. That doesn't look like a 1 to me. Since it's either R or C, it is not C, right? So once you eliminate the possibilities, whatever is left, no matter how, remember the exact phrasing from Sherlock Holmes, but whatever is.
Once you eliminate the possible, whatever impossible remains. No.
After you eliminate the impossible, whatever is left, no matter how absurd it looks like, has to be the answer. Something like that. I'm paraphrasing, but that's logic, okay? Because once we know there are only 2 possible choices, and it cannot be this one, it's got to be the other one. So S of I is R of Q of I, K of I. That is pretty cool. Because now we can figure out structurally, we can figure out the Q row, we can figure out the S row. There's only one row that we have not figured out yet, which is the K row, okay? So the K row is a little bit interesting. Let me pick a different color here. Because this one is because of 7 plus 8 as a carry. But this one here is because of 9 plus 1. So that means, there are two ways to end up with a carry of 1. Is that okay? So if I want to express, wrong color. Let me change that back. So if we want to express k of I plus 1, we know that one source, is coming from something about xi, yi, and then the other source is something about qi, ki. Okay, so the first thing we want to do is to figure out, what do we put here, C or R? What do we put here, C or R? C, okay, because C comes from carry, so is K. All right, so we kind of know that, okay, we figured this part out, but how do we combine these two? Because K of I plus 1 is a single value. And then each one, C of xi, yi, it can be 0 or 1. And then C of qi, ki can also be 0 or 1. So the question is, now we have two things, each one can be a 0 or 1. How do we combine those two components into a single value, which is also just 0 or 1? Well, you guys can name some possibilities. Okay, so I'm not looking for the perfect answer here, just give me some possibilities. Yeah.
Like you think more?
Together.
Or statement.
Or, okay, or will work. Okay, and what else will work? Plus addition. So addition will work here. Okay. So let's try this out. Okay, this is just regular addition here. So regular addition is going to work because there's one thing about the carry function, or about k of I plus 1, is only up to one of these two can be 1. In other words, if C of xi, yi is a 1, then C of qi, ki cannot be a 1. And vice versa, if C of qi, ki is a 1, then C of xi, yi cannot be a 1. They cannot both be 1s. Can they be both zeros? Yeah, that's pretty easy. Just make everything, just make xi, yi, qi, ki all zeros and easy. Yes, so they can both be zeros, but they cannot both be 1s. All right. So for those of you who are interested in why they cannot both be 1s, okay. So this is something that I want to kind of talk about a little bit. I know it's not entirely related to this class, but I think it is important to talk about. So let me go back to the notes here, because I wrote a very specific note to explain why that is the case. So if you scroll down a little bit, you will find using OR to combine carries. That's the explanation. It is a mathematical explanation of why we can use addition, but we can also use OR. And the reason why that is the case is both being 1s would not happen. So that's not the main focus right now, because the main focus is still going back to binary addition here. So getting back to Zernal, which is the picture that you're seeing here. This is good. Okay, if there's anything that is super important out of today's lecture, it's going to be this. Okay, now I know if you just give me the digits of x and y, I can figure out the q, I can figure out the k. But once I figure out the q and the k, I can also figure out the sum, which is the answer that I really want. What is the sum of x and y? Is that okay? And the equation that we have so far, okay, let me show you the equation. That's in the browser, but I cannot remember which one. Okay, so these two functions here, which you can also look at as equations, that works for base 10, right? How do we know this works for base 10? Because it's mod 10 for 1 and then greater than or equal to 10 for the other one. right? So that constant, okay, let me point out which constant. So the constant of 10 over here and also here means, these two functions are specialized to deal with single digit sum of base 10 addition and and the carry of adding two single digits also in base 10. Is that okay so far? So do you guys see how, okay, let me go all the way back, because I think if you understand the structure of how I make the material, it will it's a roadmap of how to understand the material. We started off with base 10 multi-digit addition. It looks a little weird because we have the Q row that you normally do not keep track of. Okay, but other than that, it's like, yeah, we kind of know what's going on. So from that, we generalize into symbols. Okay, so instead of looking at specific digits, we go like, okay, so the 3 digits of x is x2, x1, x0, and blah, blah, blah. So now we try to look for the generalized relationship between the digits. If I give you these, can you figure out the rest? Do you see the transition? Specific example to variables. So we are trying to generalize. But in order to figure out how Q is related to X and Y and how S is related to Q and K, I went back to define the functions C and R. So they help to get a job done. So once C and R are defined, at least for base 10 in this case, then I go like, oh, so with R and C defined, I can now express Q of I in terms of Xi by I. I can express S of I in terms of Qi Ki. I can also express K of I plus 1, which is the one in the next column, in terms of Xi by I, as well as Qi Ki. That is the structure. Okay, so I have extracted the structure of multi-digit addition. But then people will be saying, but that only applies to base 10. Well, yes, up to this point it is. But if you go back to the the definition of R and C, how do we make this work with base 2? Change the 10 to 2, exactly. But remember to change both of them, right? That's it. So from base 10, through the analysis of the process, extracting the structure, we can now just say, oh, to change the base, easy peasy. Just make this a constant, okay? Define the constant somewhere else, okay? If I make this a 2 and also make this a 2, then we have just figured out base 2 addition. But that's not the final answer yet, because we are still relying on addition here to figure out addition. That's circular reasoning, not good. So later on, okay, binary addition has some really kind of special property where we can say, oh, if this is dealing with base 2 and base 2 only, I don't need addition. I don't need comparison like this. I don't need another addition over here. I don't need division here. I can boil everything down to Boolean operators. That is something that I cannot talk about today because we are running out of time. But before Thursday, before the lecture on Thursday, I would like you guys to read as far ahead as possible, at least to the point where you can see how we can replace the arithmetic operators with binary operators. But don't go yet, because I need you to write down the passcode of your lab activity, which is base conversion. So for base conversion, the access code is arrival. That's why we are talking about base 7. Where's the connection here? Arrival and base 7. Obviously, the professor has a lot more time to watch movies than you guys do.
The heptapods of the movie.
The heptapod from the movie Arrival, yes. Yep, it is a fantastic movie. But you can also think of octopus that is using one tentacle to hold the beer and then using the other 7 to do the calculations. That would still be base 7 because I need to hold on to the beer. All right, so you guys can go. I'm going to reset the time. so that you guys have until 8:20 to get everything done today.
For speaking who test, right? Like time, take a test, quizzes test or no?
We typically don't have quizzes, but we do have exams. At about one per through and then two per through the semester, and then one final exam. I typically don't do quizzes, because it's taking up time and, but I would give you guys some in-class problem and we'll solve together. Okay. All right, so to the people who are online, we are transitioning to the lab right now. So I will see you guys all at the lab. Whew, that was loud.
I have to say, this is pretty cool.